Welcome back to geometry. Today we're going to take a look at section 12.4 and we're going to move on to the next geometric measure. We spent a lot of time now talking about surface area, so now we're going to move on to another three-dimensional measure called volume. And you can see the definition there on the screen. Volume is going to be defined as the measure of an enclosed space. And so we use the word space to represent anything that's going to be three-dimensional, right? And then the notation that we're going to use is when we give an answer to a volume question, we're going to measure that in what are called cubic units. So it might be cubic meters, cubic inches, cubic feet, cubic centimeters, whatever cubic miles, whatever labels we might happen to be in. But we're going to use the power of 3 to remind us that we're measuring something that's three-dimensional. Okay? Now, to accomplish this, we have some kind of elementary school ideas that we could use. All right? And an elementary school idea would be to create a shape out of little blocks, whether they're cardboard blocks or wood blocks or whatever, maybe even sugar cubes. And we could calculate the volume of the shape that we create by counting the blocks. Now, you might think, well, that's not very difficult. I could just start counting them and numbering them, so I could count 1, 2, 3, 4. But some of them are kind of hidden in the picture. So you might resort to a method like this. Well, the column I just highlighted, right, this column right here, let me put a red arrow on it. That column of blocks has 4 cubes in it. 1, 2, 3, 4. And then if you actually count how many of those stacks of 4 that we'd have in the picture, there's the first one. We have another one there, another one there, another one there, another, and another. So we have 9 stacks of 4 blocks. So you might think, well, 9 times 4 would make 36 blocks. And then are there any other blocks that aren't accounted for? Well, we have this fella right here. We have one more block that's all by its lonesome. So what we'd have to do then is add 1 to the 36. So our total then would be 37. And what we'd start to call that then is the volume of the shape. And whatever, there's no measure on this. We don't know if these are inches or whatever. So we could then call this cubic units. Okay? So that would be something we may have done in elementary school. And then in the second example that you see down below, the idea would be to take a shape like this and kind of do the same thing. Do something similar, but maybe just imagine it to yourself. They give you the size of all of the different parts of this weird L shape. But you could actually think to yourself, well, I could start cutting these into cubes. It's just kind of tough because everything's at an angle, right? And then start creating these stacks, all right? Like here we'd have stacks of 5. All right, so we'd have 16 stacks of 5. So you'd think, well, 16 stacks of 5 is going to get me to, what is that, guys? 80. So that whole left-hand side of the picture would consist of 80 blocks, 80 cubes. And then the shorter, lower part over to the right is 5 in one dimension. So you can think about having 5 coming across this way. My angles aren't very good there, but I think you get the idea. And then 4 going the other way. So 4 coming this way. And then all of these would be too tall. All right, so all of these little stacks would be too tall. So there'd be 20 stacks, 5 by 4. And then, so 20 stacks altogether. And then each of the stacks would just have 2 blocks each for a total of 40. So the left-hand side of the picture would have 80 blocks. The right-hand side of the picture would have 40 blocks. So altogether, what we would then call volume, the total, would be 80 blocks plus 40 blocks, so 120 blocks. And again, whatever the units are, so we'd write it as units cubed. Okay? But that's kind of a hassle. That's kind of difficult to do. So instead of just trying to think of all of the pictures as being blocks, instead what we're going to do is we're going to use formulas. Okay? So we're going to use formulas to find volumes. And we're going to start with two shapes in this section. We'll start by looking at volumes of prisms, which we've defined earlier, and the volume of cylinders. Okay? Now, first one, theorem 12.6, the formula for the volume of a prism is B times H, where B is the area of the base, and H is the perpendicular height. Okay? And then theorem 12.7, the volume of a cylinder is B times H. Same, base times height. But because a cylinder specifically has a circular end, whoop, that's a terrible, let me try that again. Make that look a little more rounded. Yeah, so that looks a titch better. Because the base on every cylinder is a circle, we have another version for the formula if you want. You can write both of them down if you wish. So we could also think of the volume of a cylinder as pi times r squared, because that's the area of a circle multiplied by the perpendicular height. Okay, so if you want to write both of those down, that'd be great. If you just want to write down B times H, that's also fine. Okay, now let's take a look at some examples of how we can calculate some volumes. Okay, so here's a triangular prism. All right, so again, just going back, that's a prism because the front triangle and the back triangle of this prism are the same size. So if we wanted to calculate volume, the formula again is going to be B times H. B represents the area of the base, so that would be the area of this triangular front. And since it's a triangle, we know how to find the area of a triangle. That's 1/2 times base times height. Now we can see from the picture that the base of the triangle is 8, and the perpendicular height is 6. And then what we have to do is multiply by the height between the two bases. And you can see that in the picture. The height between the front of the prism and the back of the prism is 4 meters. So what we have here is area of the triangle, and what we have here is the height between the front and the back. And when you guys do the math, the area of the triangular base is 1/2 times 8 times 6, which is 24. And then 24 times 4 gives us 96. And you can see the units in the picture are meters. So our volume then would be 96 cubic meters. All right, try another one of those. Now this one appears easier because it's just a rectangular box, so a rectangular prism. But I wanted to jog through an example like this for one reason, just as a reminder. Again, volume is going to be equal to base times height. And I just wanted to do a simple rectangular prism because I wanted to remind everybody that with certain shapes, like rectangular prisms, you really have a lot of choices as to what side you consider the base. All right, some people like thinking of it as the top and the bottom. Other people like thinking of it as the front and the back. It absolutely doesn't matter. As an example, if we were to think of the base as being the front, then to calculate that area for the base, what we do is say, well, how do we find the area of that shape? That shape, of course, is a rectangle. And the area of a rectangle is its length multiplied by its width. So it's going to be 9 multiplied by 3. And then h, the height, is the distance between the front of the prism and the back of the prism. And you can see on the picture that the height between the front and the back is 7. And so when we do the math, 9 times 3 is 27. And then when I multiply that by 7, 27 times 7 is 189. So I'd have a volume then of 189 cubic inches. But somebody in class might think, well, what if I didn't consider the front to be the base? What if I considered the top to be the base? What if I called the top B? Well, then the volume, blue doesn't show up very well there. Let me pick a different color. How about yellow? Then the volume is still going to be B times H. But if we consider the top to be the base, now the area of that rectangle is 9 times 7. And the distance between the top and the bottom then is 3. But you can see we have the same three numbers multiplied together, just in a different order. So 9 times 7 is 63, and 63 times 3 is 189. So we'll get the same result, even though we selected a different base. So not a worry. Okay, now let's move on to one that's more difficult. And it's more difficult because the base is going to be a more difficult shape to work with. The idea is still the same. We still want to calculate the, we still want to calculate the volume. So that's still going to be B times H, all right? B is the area of the base. Height is the distance between the bases. But the issue here is the base is a regular hexagon. So what we're looking for with B is the area of a regular hexagon. And now we've got to go back to the last chapter to remind ourselves how to find that. The area of a regular hexagon is going to be 1/2 times the apothem times the perimeter of that base. And then, of course, we'll just be multiplying by the distance between the bases, as it's called the height. Okay? So from the picture, can you guys clearly see what the apothem is? No. Can you clearly see what the perimeter is? Well, I think you can there, because the side length of the hexagon is 8, and since all of them are the same, all of the sides would then be 8, going all the way around this fella. And so the perimeter is just going to be 8 plus 8 plus 8 plus 8 plus 8 plus 8, or 8 times 6. So the perimeter is going to be 48. Now also from the picture you can see the distance between the front hexagon and the back hexagon is 5. So the only number we're really missing is the apothem. And I just need to remind everybody that the apothem is the distance from the center of the hexagon perpendicular to any one of its sides. That's called the apothem. All right, and does everyone remember how to find that? Well, I hope so. The idea again is to draw in a whole bunch of the radii. You can put them all in if you want to, or you can just put in some. It's just totally up to you. Okay? And then what we'd have to do is calculate one of the angles at the center. So it's going to be a complete rotation divided by the number of angles. So every one of the central angles is going to be 60, looping all the way around. And now, before we get going, since each of the yellow lines I've drawn in is a radius, those would all be equal to each other, right? Because the radii, I guess I should say, are all going to be equal. And what that makes every one of the triangles then is that makes every one of the triangles equilateral, because it'd be a 60, 60, 60 degree triangle. So 60, 60, 60 is equiangular, and equiangular triangles are always equilateral. So that means if the bottom, the side, is 8, all of the radii would be 8 as well. And now if I just pull one of those triangles out, this side would be 8, this is the apothem, and this side is 4. Remember, when we draw the perpendicular, it always cuts the bottom into 2 equal chunks. So therefore, we can find A using Pythagorean theorem. So it's going to be a squared plus 4 squared equals 8 squared. And then when you start doing the math, 4 squared is 16, 8 squared is 64. Subtract 16 from both sides and take the square root of both sides. And let me punch that out for you guys. The square root of 48 is going to be about 6.8 or 9, 6.9. So the apothem then is 6.9. And now I can fill that into my formula for A. And we're all set then to calculate the volume of this shape. I'll get you the area of the base first. So 1/2 times 6.9 times 48 is 165.6. And then multiply that by 5. And we get approximately 828 cubic centimeters. And that would be the volume of this hexagonal prism, right? Hexagon on the end, prism. Okay, so that's a tough one. Feel free to pause this part of the video if you want to take a closer look at that. Otherwise, I'm just going to move on to an easier one, the volume of a cylinder. Okay, now again, the volume of a cylinder is going to be the same as the volume of a prism. Whoop, I don't need parentheses there. It's just going to be the area of the base times the height. But since the base is a circle, we could then write that, if we wanted to, as pi r squared, area of a circle, times h. Okay, and then from our picture, you can clearly see the values that we need. You can clearly see the value for r is 3, and the height of the cylinder is 4. And so I'll give you the exact value and the approximate value. 3 squared is 9, and 9 times 4 is 36 pi. Or if you'd rather have the approximate, meaning use your calculator, we get about 113.1 cubic feet. So cylinders are fairly easy. Cylinders are fairly easy to work with because there's only 2 values you need, the radius and the height. Okay, so 2 other problems then that we want to be able to do. All right, one is finding the volume of a solid that has a hole in it. So what I've shown you, forget about the formula for 1 second. What I've shown you is a rectangular prism, a box. And then what we're going to do, guys, is we're going to pretend to take a drill bit and maybe like, I don't know, even something easy like a spade bit. I don't know if you guys know any woodworking. But what we're going to do then is we're going to drill a hole in, let's go through the top. So we drill a hole through the top all the way through the bottom. Okay, so we started with this rectangular prism, but then what we did was we drilled out this hole all the way from top to bottom. And the question would then be, once we clear away the wood chips, what would be the volume of what's left? And so the idea is going to be to find what's called the net volume, meaning the volume of what's remaining. What we do is we start by taking the volume of the hole shape, the volume of the rectangular prism, and then subtract away, because we're drilling it out and throwing it away, we subtract away the volume of the hole. Okay? So that basic idea leads us to problems where we end up with some strange looking shapes like this one, where we have a big cylinder to start with, and then we take like a big Forstner bit, I guess a gigantic Forstner's bit, and drill out the middle of this. And so what we end up with is something akin to, I don't know if you guys know what a bushing is, but it'd be something similar to a bushing, or just kind of a, just this circular 2-inch material going around in a loop with a big hole in the middle. And what we're going to challenge you guys to do is find the volume of what's left over when we've drilled out that 7-inch radius hole from the middle. So the idea is going to be the net volume, what's left over, is going to be equal to the volume of the hole minus the volume of what we drill out. All right, and I tried to mess with you guys a little bit, get you to smile a little bit. I used the word hole twice. I was hoping someone would call me, give me some grief about that. But anyway, we take the volume of the hole shape and then subtract away the volume of what we've drilled out. Okay, so what is the volume of the hole shape? Well, it's just a big cylinder. You just have to be careful. What would be the radius of the big cylinder? Well, it would be the 7 for the interior part of the radius, and then the 2 extra inches to get to the outside. So a total of 9. So the original radius for the big shape is 9. And then of course you see the height between the top and the bottom is 5. Okay? And then the part that we drill out is also a cylinder, so we're removing another cylinder, but this time the radius isn't 9, it's 7. So the radius this time is 7, but the height is still 5. Okay? And so when we do the math on this fella, what we get as an exact answer is 405 pies minus 245 pies. So 405 minus 245 would leave us with 160 pies. And I don't quite have enough room, so I'm going to have to do this off to the side. Sorry about that. Or if I punch that out on my calculator, which I know some of you guys would prefer, we get about 502.7 cubic inches left. So the net volume would then either be 160 pi cubic inches or about 502.7 cubic inches. Okay? And then the last problem for this section is one like this, where we tell you the answer to the volume question. We actually find the volume for you. And then what we ask you to do is find one of the pieces that's missing, and we use a variable to represent it. So as an example, in this triangular prism situation, I tell you what the volume is. I say, hey guys, here is the volume. Can you tell me the height of that prism? So the idea would be to start with the formula. The volume is equal to base times height. Now in this particular case, the base is a triangle, so that's going to be 1/2 times the base times the height. All right, and what we're missing here, guys, is the distance between the top and the bottom. Okay, so do we know the base and the height of the triangle? Remember, those are perpendicular to each other. So since here is the 90-degree angle, those are the two sides that we need. Now, because this lower value is 8, I could transfer that up. But what we're missing is this side. So what I would have to do in this situation is call that a question mark for a second, and then use Pythagorean theorem to find that missing piece. So it'd be 8 squared plus question mark squared is equal to 17 squared. All right, 17 squared, is that 289? Yep, so that one's 289. And then what we'd have to do is subtract 64 from both sides. So that makes it 225. And then to take the square root of both sides, the missing side then is 15. And therefore, the base of the triangle is 15, the height of the triangle is 8. And again, we're told the volume, so I can actually use my deluxe eraser, and I can remove the volume and replace it with 360. So if I do a little calculator work, 1/2 times 15 times 8, we would get 60. And then to solve for x, I just have to get rid of times 60, so I divide by 60. And so the missing piece, x, is 360 divided by 60, which would be 6 feet. All right? And so we'll ask you to do a few of those where we give you an answer to a volume problem and then ask you to find one of the missing measures. A height, a base, whatever a radius may be. We'll ask you to find one of the missing pieces. Okay, so that's it for section 4, so you should be able to stop this video and then open up your book and start working on the problems. Let me know if you have any questions. I'll try to help you out either by email or phone. Just give me a holler. Okay, hope you're having a good day. Talk to you soon.